So that's the something that has a unique situation when your external pressure. It's called a free expansion when there's no work done by the system, and this is going to be happen this way when things are isothermal. This is a very unnatural process. Okay, isothermal expansion. But when things are the expansion, you think about expansion means I'm doing the work, but irreversible when external pressure is zero, there's no work, so you're not losing anything. You just make this gas molecule fall apart without doing any work, but there's no change in internal energy, so everything is the same. No heat is needed to compensate those changes. What's my delta total here? Delta S plus delta surrounding. Same as this. NR BF BI. And that's a so that is one. And then this is a one positive. Right? So total system, total entropy is in a direction for the increasing it, and that's what this is. And this one, this is true. And because of the external pressure, the reversible, when work is irreversible, and work is reversible, and you have delta S, so 0. That's what this is. 4. The textbook didn't explain that much about why this has to be 0. But what their statement is, when the adiabatic process, whether when system, this is a case. I can imagine the same thing because all those things are irreversible. Q is a 0 here, and when Q is 0, as being defined, so in this case, in the last row, that's an adiabatic process, and things are adiabatic, and further is an irreversible adiabatic process. So this is, by definition, is 0. And I can convert that philosophical argument that as far as the system is my surrounding, this is done in always a reversible way. So this is always true too. Okay, so that is a 1. And so therefore, this is the only thing that I have an exact relationship. This one in and that is, this is all I got. I cannot go beyond it. I don't have an equation. So I guess one thing that I can add it on is delta S surrounding is 0 when adiabatic. System is adiabatic. Whether it's a reversible or irreversible, we know the system, the surrounding entropy change is 0. So that's one other thing that you can see this. Okay, so that's the one I highlighted here. One thing to know. These are the easy one because this is a reversible. Okay, because they are reversible, we can know that. And because it's adiabatic, surrounding is 0. And then the rest of the one, delta S here and here. This is probably the most important one they emphasize here when you have those. That's regardless of how the process has happened. If the system defines the initial state and final state, we can always kind of change the problem around and make it something more easier to derive, and that's what this is. And this is a, I think this is a very special case, okay, for when work happens to be 0, Q is 0. Okay. So if this is non-zero, and I have no idea what it is, right? So therefore, I don't get this equation either. So if you look at my class note, there is a more elaborate one, and the last page is about the table, so you can see that as well. I would like to really move on to the next one today. So by using the table, just going directly, it's a little bit messy, but I think that you can have a better sense, and then please go back to the notebook and have a much more cleaner writing here. But can you get a really good snapshot on this? Those are the full process that we are dealing with. And then as far as the Carnot cycle is concerned, which is the next one that I'm going to talk about, it's all about reversible. And it's a combination of isothermal and adiabatic. And then we're going to drive that, and that actually became very important. Sort of the most iconic, very simple. I mean, I can do one blackboard, I can get all the quantity that I want, and it will be very, very useful concept that we want to deal with. Okay.